Thank you for joining for this presentation of a survey of the state of explainable AI for natural language processing done at IBM Research. Traditional NLP techniques have been inherently explainable: rules, decision trees, logistic regressions, and so on. In contrast, recent advances have been primarily black box techniques, such as deep learning models or using language embeddings as features. But while these methods in many cases substantially advance model quality, they come at the expense of models becoming less interpretable. In this regard, explanations can help users of NLP-based AI systems build trust in these systems' predictions. Additionally, understanding the model's operation may also allow users to provide useful feedback, which in turn can help developers improve model quality. Explainability is in itself a term that requires an explanation. The role of an explanation may be to reveal model behavior, for instance by comparing the predictions and evidences of two different models. It could also be to justify the prediction of a model on a specific instance, or else it could be to help humans investigate low-confidence predictions, for example, by providing evidences and counter-evidences. The focus of this survey is the second, explainability from the perspective of an end user whose goal is to understand how a model arrives at its result, also referred to as the outcome explanation problem. We aim to provide a framework for understanding the recent advances of XAI research in NLP rather than an exhaustive list of papers. To create a reasonably representative pool of work, we identified papers published from 2013 to 2019 in 4 major NLP conferences with titles that somehow mentioned XAI terms. We then analyzed and classified each paper, yielding 50 papers with a focus on explainability as a vehicle for understanding how a model arrives at a prediction result. Our methodology was guided by our goals for this survey. The first goal is to provide an understanding of the current state of XAI in NLP, including to serve as a practical guide to existing explanation techniques for the interested developer. The second goal is to highlight a current lack in several important aspects: clear terminology around explanations and the intended target audience, standardized evaluation processes and metrics, and breadth of evaluation of different explanation aspects, such as fidelity and comprehensibility. With these goals in mind, the rest of this presentation, as well as the paper itself, which contains more details, is organized around how XAI in NLP answers the following questions: what is being explained and when? How is the explanation derived and presented? How successful is the explanation? And finally, what's next for XAI in NLP? Explanations of model predictions have previously been categorized in a fairly clear but simple way to answer what is being explained and when. The first half of the question, what is being explained, differentiates between whether the explanation is providing information or justification for the model's prediction on a specific input, or revealing something about the model's predictive process independent of any particular input. This is the local versus global axis. The second half of the question, when is the explanation generated, distinguishes between producing the explanation from the information emitted by the model as part of the predictive process, or creating the explanation via a separate process of additional operations after the model has yielded a prediction. This is the self-explaining versus post hoc axis. Combining these aspects yields the common explanation categorization axes. We found that within our sample, explanations for 11 papers were local post hoc, for 35 papers were local self-explaining, 3 papers were global post hoc, and just 1 paper was global self-explaining. The low number of global explanations is not surprising, given the focus of this survey being on explanations that justify predictions, as opposed to explanations that help understand a model's behavior in general. To put some of these numbers into context, let's consider a couple example papers. Here are 2 local self-explaining papers. On the left, Gaini et al. Addressed the task of textual inference. Attention saliency and LSTM gating signals yield prediction feature importance scores, which are presented as a heat map to serve as an explanation. On the right, Abu-Jabal et al. Tackle question answering, responding to natural language input by showing the constructed query and the knowledge base provenance that lead to the returned answer. While in both cases, an explanation for a single prediction is calculated from information available from the model, there are clearly important differences in the techniques and goals for the presented explanations. Next, let's look at two local post hoc papers. Wallace et al. And Crochet et al. Both use post hoc explanations, but where the former uses first derivative saliency to enable word-level feature importance presented by highlighting text, the latter uses layer-wise relevance propagation to enable example-driven explainability, shown to the user by comparing their input query to a training data example. Working through our literature review, we try repeatedly to extend the common axes of local versus global and self-explaining versus post hoc into a well-organized taxonomy. However, the numerous observed combinations of the explanation techniques, the operations that enabled the explainability, and the visual presentation to the user would not fit nicely. So we came to the conclusion that we had to alter our approach. Thus, while the previous categorization serves as a convenient high-level classification of explanations, it does not cleanly align with the more focused and practical questions of how is the explanation derived and presented, which is where we turn our attention now. Why differentiate between derivation and presentation? Because they're in fact separate aspects that are combined differently across various works. Explanation derivation focuses on the mathematically motivated justification of model outputs, leveraging various techniques to produce raw explanations. The subsequent presentation step focuses on showing the generated explanation to end users, using suitable visualization techniques. We now offer a brief description of the most commonly used explainability and visualization techniques in our NLP paper set. We begin with explainability techniques, which differ in the mechanism used to generate the mathematical justifications of predictions. Feature importance investigates the importance score of features used to output the prediction. For example, the contribution of individual characters in a morphological tagging task. As text-based features are inherently more interpretable by humans than general features, this technique is widespread in the NLP domain and is usually enabled via first derivative saliency or attention mechanisms. A surrogate model is a second model that is learned as a proxy, which is usually more explainable but carries concerns about fidelity, since it may have a completely different prediction mechanism from the first model. This technique's popularity has increased as more NLP papers employ neural network-based models. It may be enabled by the input perturbation technique, pioneered by the well-known Lime paper, or by an explainability-aware architecture design. Example-driven approaches explain the prediction of an input instance by identifying other instances, usually from available labeled data, that the model judges to be similar. They have been applied to various NLP tasks, such as classification and question answering. Provenance-based explanations expose some or all of the prediction derivation process and are frequently seen in question answering tasks. Finally, declarative induction explanations induce representations, such as rules or programs. We will now move on to visualization techniques, which describe how the explanation may be presented to the end user. The most dominant technique we encounter is saliency, which can refer to visualizing feature importance scores as a heat map, for example, displaying extracted relations, or highlighting words in the input instant text. Papers that use feature importance to generate explanations therefore usually choose a saliency-based visualization, which are generally understandable by most people, but we also see some surrogate models visualized in this way. Raw declarative representations directly present learned declarative induction rules or programs, and therefore may implicitly target more advanced users who are able to understand them. Another common visualization in NLP is, of course, to verbalize the explanation in natural language. This may be created using a deep generative model or even simple template-based approaches. In fact, raw declarative representations may be transformed into more human-readable language using template-based techniques. Our literature review uncovered a variety of combinations of explanation aspects, resulting in a richer and, we believe, more practically useful view of the state of XAI and NLP, beyond the high-level categorization of local versus global and post hoc versus self-explaining. And we hope you see our survey for full details. Following the goals of XAI, a model's quality should be evaluated not only by its accuracy and performance, but also by how well does it provide explanations for its predictions and how successful those are. But these model characteristics may often be at odds with each other, with, for example, more complex models achieving better predictive power at the expense of slower runtime. Given the young age of the field, unsurprisingly, there's little agreement on how explanations should be evaluated. The majority of the works reviewed either lack a standardized evaluation or include only an informal evaluation, limited to discussing how an example of an explanation might align with human intuition. Several works compare generated explanation to ground truth data, employing metrics such as F1, perplexity, and BLEU score. Creating ground truth data is frequently a challenge here, both in ensuring its quality and accounting for cases where there may be alternative valid explanations. Yet a smaller subset of papers assess explanation quality using human evaluation, either rating the explanations of a single approach or comparing across multiple techniques. This sidesteps the problem of quantifying explanation similarity, but instead requires researchers to correctly deal with subjectivity and variance in human responses. A more general point is that explanations are multifaceted objects. They can be evaluated on multiple aspects, such as fidelity, how much they reflect the actual workings of the underlying model, and comprehensibility, how easy they are to understand by humans. Understanding the target of the evaluation is important for deciding how to measure and interpret evaluation quality, and there's a significant amount of research that remains to be done in this direction. Another important and often overlooked aspect of explanation quality is the part of the prediction process covered by an explanation. As an example, consider the math QA task of solving text math problems. On the left, the explanation of Amini et al. Provides only partial coverage, showing the sequence of mathematical operations leading to the answer, but not explaining how these operations were derived from the input text. Arguably the lion's share of the work. Your high school math teacher may not have given full credit for such an answer. On the right, see how Ling et al. Augment the mathematical formulas with text describing the thought process behind the derived solution, thus covering a bigger part of the prediction process. However, the value add of this information does very much depend on the target audience and the end use of the explanation. So this must be realistically balanced against the complexity that may be involved in obtaining higher coverage. We would like to conclude with a brief comment on what we believe to be important avenues for XAI research in NLP. We hope this survey encourages the research community to work in bridging the current gaps in the field. The first research direction is a need for clearer terminology and understanding of what constitutes explainability and how it connects to the target audience. As in the math problem solver example, how explainable and for whom is a model that displays an induced program for yielding a prediction but conceals the induction process? The second direction is an expansion of the evaluation processes and metrics, especially for human evaluation, and assessing the trade-offs between performance and explainability as desired model characteristics. The third direction is a call to more critically address the issue of fidelity and to ask hard questions about whether a claimed explanation is faithfully explaining the model's prediction. Thank you for listening, and please visit our accompanying website to investigate our survey findings interactively.